Okay, so we have to have a picture. We have to have a good picture. So let's sketch this. So and then you can use your graphing calculator if there's something you can't sketch quickly. But let's make a sketch here. So y equals, wow. Okay, y equals 2 sine x, something like this, between 0 and pi. And then 4 cosine x is going to be up like, starting up here, say, and going like this. Okay, and then between 0 and 0.7 pi. So 0 is here, and 0.7 pi might be something like this. Okay, so it says enclosed between those curves, and then from 0 to 0.7 pi. So we have to get the region right, or else we'll be dead in the water. So in between those curves would be, starting at 0, in between would be, say, in between here. So here, like this. So we're going to have this part here, and so a typical strip. The other thing I noticed, you guys, no one did typical strips. Okay, when we get to the volumes, it's going to be crucial. So there's a typical strip, but then when we get to this point right here, it changes, right? And so now a typical strip looks like this.
What do you mean no one did typical strips?
Just no one. You just went right to writing an integral.
How do you know?
The people that came for me to help.
Oh, okay.
Just some people that came for help. This is the pattern that I noticed. You just went right to writing no picture, and then went right to writing down an integral. And a complicated problem like this would be very, very difficult to get it right without these things. These are, like I said, these are geometry problems. So you need that picture, and then just get in the habit of doing a typical whatever, okay? Because we're going to see this for the next week or so, doing all these integrals. It's all about summing up some typical quantity to get the total amount of that quantity. Okay. Integral means sum. German S. It means sum. You're summing up something. You got to know what those things are that you're summing up. Okay, so then this region between the curves is actually two regions. Region 1 and then region 2. That's what you have between the curves. So we're going to have two integrals. We're going to have to find this intersection right here. And we can get that intersection by setting the y values equal. So 2 sine x equals 4 cosine x. Okay, and so then sine over cosine would be tangent x. In my problem, tangent x equals 2. So I can do sine divided by cosine and 4 divided by 2. So this point, this x value is the arctangent of 2. That's that x value. That's the breakpoint or the intersection point. Okay, so then we're going to have the integral is going to, so this typical strip here, what's the area of that? The area of that is base times height. And the base is what? What's the base?
Delta x.
Delta x. What's the height?
y2
Yeah, y2 minus y1. So let's go right to what those x are. So what is y2? y2 is 4 cosine x. And y1 is 2 sine x. So the area of this typical strip is delta x times 4 cosine x, 2 sine x. That's the area. And so that's what I'm adding up. I'm adding up a bunch of those. As what? As delta x gets very, very small. And so what is that when delta x gets very, very small? So from 0 to arctangent 2. Arctangent 2, I'm summing up a bunch of rectangle areas. Each one of those rectangle area is this. So 4 cosine x minus 2 sine x. But now the base is just really, really thin. So instead of delta x, it's, yeah. So see, notice the dx is not just an afterthought. It's not just, oh, we always put a dx on when you do an integral.
Yeah.
Right? It has mathematical meaning. What is it? What is that mathematical meaning? It's the width of the rectangle, right? We're doing an area of a rectangle. Base times height. That's the base of this rectangle, of which we're adding many, many, many together. You see? So it's not just, oh, you always need a dx when you do an integral. It just did it. No, it has a mathematical, it's the width of the rectangle, which we need for the area, right? So that whole thing is a dA. dA is an amount, that whole thing is height times base, or dA, for a rectangle. And we're summing up a bunch of dAs. But if you just go right to writing the integral, you just kind of like, oh, this is the pattern. You did an integral of the function, and then you tack on a dx. You lose all the meaning, right? You lose all the meaning. Okay, and then we're going to go plus integral. Now we're going to start at tangent inverse of 2 up until 0.7 pi. And now our typical rectangle is going to be, again, base times height, delta x times. Well, now our top function is sine, 2 sine, minus the bottom function is the 4 cosine. So they reverse. So then it's 2 sine x minus 4 cosine x dx. And then you just got some algebra to do. Antiderivative, it kind of gets to be a long expression. You just got to be careful. But remember, in web work, you can enter in expressions, right? You can enter in an expression with 8 terms here. You can have 8 terms. Right? You can have 2 from the first integral, but then you're going to be plugging in 2 values. And you have 2 for the second, and you're going to be plugging in 2 values. So that makes a total of 8 terms. You can just write the whole long expression out if you want in the web work entry bar. Questions on this one? Ask. Please ask. There were lots of people who didn't get this, so I lost you. Everybody good? Can I erase and go on to the other one, which I think was 6? What was 6? Oh, the tangent line. Okay. So now you have to draw back on some stuff from Calc 1 here. So you got y equals 3x squared, and then the tangent line at 212. So here's 212, say, and then there's a tangent line that. And you want to find, there's your, so the area bounded by the parabola, the tangent line, and the x-axis. So we're looking at this thing right here. Okay, so a big common mistake that students make is that they will They will inject an axis, either the x or y axis, into the description when it's not there. Okay? This one says the x-axis. Okay? So that's going to be one of your boundaries, but be careful about that. If it doesn't say x or y axis, then the x or y axis is not one of your boundaries. It's easy just to say, oh, you just, like, you draw the picture of all the curves, and then this region just pops out at you. You say, oh, it must be that. Okay, so, but not necessarily. If it doesn't say x or y axis, and the region you picked is using the x or y axis to be part of the boundary, then it's not right. But anyway, this is this one here, like this. Okay, so how are we going to do this? So we could do delta x or delta y. Is there a good choice? Is there a difference? If we do delta x, what happens? So we've got these typical strips, right? It switches. Do you see that it switches? A typical strip over here on the left is different than a typical strip over here on the right. So if you're going to do delta x, or vertical strips, you would need to add together two integrals. Does everybody see that? But what about delta y? Can you do it in one? Yeah, the whole way from the bottom to the top, you have the same typical strip. Its left side is this curve, and its right side is the tangent line. And that's the same typical strip for the whole way up, from the bottom up to the top. So we can do it in one integral if we do delta y. So area of the typical strip is base times height. Okay, the base is going to be from, yeah, it's going to be a difference of x's, right? It's going to be x2, which is defined by our tangent line, and x1, which is defined by our curve. And then the height will be, what's the height of that typical strip?
Delta y.
He wants delta y. Agree with that? Okay. So x2 is this tangent line. x1 is going to be just solving this thing for x in terms of y. So we need to get the equation of this tangent line. And so now you have to kind of review or brush up on your calc. All right, so what do we need? We've got a point, so all we need to get the equation of that line is what? In addition to a point? Slope, or rate of change. So what do we need? We need the rate of change of this tangent line, which intersects that curve at x equals 2. So how do we get rate of change? Derivative. dy dx is the rate of change, 6x. And we're going to evaluate that at x equals 2. So we have a rate of change, or a slope, of 12, and a point to 12. So you've got, I can do y minus, so you got the point and slope, so one way to do that would be to say y equals 12 times x minus 2 plus 12. Both the slope and the y value are 12, I guess. But now we need x in terms of y. So that tangent line has that equation. And so solving that for x, we'd have y minus 12 over 12. So first subtract 12, then divide by 12, then add 2. And that is what? That's our x2, right? Our x2 was this tangent line. And then our x1 was the curve. So it'd be y, square root of y over 3. So this is our x1. here for the left side of the strip. So then this, the integral would be, the area would be the integral from,
From 0 to 2.
yeah, so in terms of y, it'd be 0 up to
From 0 to 12.
0 to 12. All the typical strips start at 0 up to y equals 12. Then we're going to have the x2, y minus 12 over 12 plus 2 minus square root of y over 3. And then these are really, really thin strips, so instead of delta y, it's dy. Okay, I went fast, but hopefully you could track with me because you worked on it, you thought about it. Yes, please.
What if you simplify that? So it's like 12x minus 24 plus 12 would be 12x minus 12. And that might make it more simple, a lot easier to.
Yeah, but you could do the algebra at the beginning or the algebra here at the end.
Oh.
It doesn't matter. Yeah, so this is y. This is y over 12 minus 1 plus 2. Y over 12 plus 1. Is that what it turns out to be?
I have 12 plus 1. It'll just be y over 12 plus 1. So it'll just be 112 y
Plus 1. Right?
plus x.
What?
Oh, I'm taking the antiderivative.
Yeah, I'm just setting up the integral. This is an easy antiderivative. So I'm just setting up the integral here.
It's going to be 12 y plus.
So 1/12 y plus 1 minus, that's your x2. And then your x1 is radical y over 3. That's a y, not a 4. Did I make a mistake, or is that right?
That's right.
That's right? Matthew?
How'd you get to the square root of 4/3?
Y over 3. It's this x2, right? So x2 minus x1 is this curve x in terms of y. So I'm just solving for x here. X is going to be y over 3 and then square root. That's a y, not a 4. Questions on this one? Yeah, Andre.
Could you go over one of the last two problems in the second set?
Yeah, we're about to do that. Any questions on areas? All right, let's look at the volumes. Looks like number 4 is the one to do here. Okay. Y equals x squared, y equals 9, and x equals 0 about the y-axis.
Could you subtract from a right cylinder to get negative space? I tried that and it was wrong. I might have done it wrong.
Yeah, you can do things like that.
But I feel like that's not what you want us to do.
Well, let's just see what's easiest. How about? So y equals x squared. Sometimes things like that make it easier, but then sometimes like that make it more complicated. But yeah, y equals 9 and x equals 0. That's the y-axis. So it's this thing right here. I'm going to go around the y-axis. Yeah, trying to... If you,
I was doing around the x. I didn't read yeah.
We'll do problems like that today.
Okay.
Yeah. So around the y. So you just had the wrong, thing.
I just didn't read the problem.
Yeah, okay. And so we're going to, here's our region, R. And can you imagine what you would have if you rotated that about the y-axis? We're going to rotate that about the y-axis. Can you imagine what solid you would have when you did that? What would it be like?
It's like a bowl.
A ball, okay. Yeah, so it's going to be like, it's going to look like this. Like a gumdrop. So a bowl, I mean, kind of has the the implication that it's empty. So this is solid, right? It's like a solid thing. It's a solid. You're gonna take that. Imagine this is on a hinge on the y-axis, and you're just gonna rotate that around, and everywhere that area touches is gonna be part of the volume of your solid. So it's like a bowl that you filled up to the top, right? With whatever, okay? Or if like it's like kind of like an upside down gumdrop. So how are we going to think about this? We're going to think about this with,
Respect to y, huh?
yep, typical strip. And whatever the typical strip turns out to be when we do the rotation, that's going to be our typical volume piece. So when we take that, just that typical strip on the y-axis, what do you get? When you rotate that thing around, what do you get around the y-axis? What kind of shape do you get?
You get a disc.
Pancake.
Not a disc.
Pancake.
Pancake.
Oh.
Yes, the rest of the world calls them discs. Yes, you're right. But you're going to get like a pancake. And so if we want the volume of the solid, how are we going to get the volume of the solid? It's going to equal, we're going to sum up a bunch of volume of pancakes, right? Typical pancakes. We're going to sum up all the volumes of all the pancakes. So we need the volume of a typical pancake. What is it? So what shape is that? What kind of solid is that pancake?
Cylinder.
It's a cylinder, right? So cylinders are pi
R squared.
r squared h. So in order to get this, we need the height of that thing and we need the radius of that thing. What is the radius? So the radius is from here to here. What does the radius equal? So you go back to your original thing here. You could use x2 minus x1, but it's easier than that. What is that distance from there to there? Simply what? It's just x. It's just x, right? Because you're to the y-axis. That's your radius. Your radius equals x. Does everyone see that? Because your center is at the y-axis, and so your radius is just your x-coordinates. It's just your distance out to the curve. Everyone see that? What's the height of a pancake? What is it? Change in y. The height is delta y. That's supposed to be. Okay, so our volume of our pancake is pi x squared delta y. But we need x squared in terms of y if we're doing delta y. What is x squared in terms of y? It's just y, right? So here it is. Look, there it is, x squared. What does x squared equal? So yeah, you can solve this for x and then plug that in, or you can just recognize, oh, it's asking for x squared. I know exactly what x squared is. It's y. So it saves you a step if you see that. So it's not wrong to solve this for x and plug in, but it just saves you work if you just recognize, oh look, it wants x squared in my volume. Well, x squared is y. So it's going to be pi y delta y, volume of typical pancake. And so the volume of the solid then is going to be the sum of all the pancakes, the volumes. It's going to be pi y. But now those pancakes are going to be really thin, crepes, right? Crepes. And then we're going to go, y goes from what to what? The first one down here is this little one with barely any radius. That's at y equals 0. Then the last one, the last typical pancake, will be at 9. Done. They don't get any easier than that. It's evaluating that integral, right? So it's all here. This is all about the geometry and the setup, okay? Okay. Those who struggled on this word work, is it better? Do you have a question? Can we discuss something to help you? Okay, so let's do some more of these, but maybe slightly with a new element to it. All right, so this is perfect. So Andre wanted to do this with around the x-axis. So let's do it. Okay, so that's perfect. That's a perfect place to start here. So what do you get? So can we draw the picture? This same region, but we want to revolve around the x-axis now. So I'm going to erase this. Can I erase? Are we good? So now I want to, taking this to the next level here. I've got my region. And I want to revolve around the x-axis. What will we get when we revolve this around the x-axis? So now you imagine that thing.
Gumdrop on the side.
You get a cylinder with
Flat
flat
side on the y-axis.
So when it gets 180 degrees,
It's like a volcano. A crater. A sinkhole. An unkissed.
so when it gets down 180 degrees, it'll look like that. So now imagine that thing is just rotating all the way around, right? So it's going to be something like this. Okay, and then it's going to have this, like this, and then this will also be rotated. Then it'll be like this. Can you see it? So if you turn this thing this way, if you turned it counterclockwise, then it would hold water, right? It would hold water. It'd be like a cup with a really weird inside shape, like maybe like it would hold a football or something. I don't know. What does that look like?
Volcano, man.
It doesn't look like a volcano.
Maybe
A volcano is like this. This is a volcano. That's a volcano.
Come in all shapes and sizes.
No, this is not a volcano.
Everyone write that down.
So it's a cylinder and it's got like a kiss cut out of it.
There you go.
It's a cylinder and has a kiss, a Hershey's Kiss cut out of it. So now, our strip, is it going to be a vertical strip or a horizontal strip? Well, it's actually, you could actually do either, okay? We're going to do a vertical strip here. Okay, we're going to do a vertical strip. And so now, again, the typical volume element comes from taking that two-dimensional strip and doing the same rotation that you're doing of the region and see what you get. So when you rotate that strip about the x-axis, what do you get? Do you get a pancake? when you rotate that about the x-axis, do you get a pancake? You get a, what's that? You get a pancake with a hole in it, right? You get a pancake with a hole in it. Exactly. Because it's going to flip down here. There's going to be that hole part in the middle that you don't get. Not a donut, because donuts have a circular cross-section, right?
It's very specific foods.
Okay. Kind of, all right? A donut that's been run over, right? Donut that's been run over by a truck, okay. Yeah, so let's draw it. So you're going to get, our typical element's going to be this. How did I do? Could be worse, could be better. Yeah, so these are, yeah, we're going to call these washers. It's like a metal washer. A little bit better. Okay, there we go. That's pretty good. Finishing touch. Okay, so we've got our metal washer. So we want the volume of a typical washer. How do we get the volume of something like that?
Y.
Volume of the cylinder minus volume for the.
You don't go to Y2s and Y. This is do in the biggest picture. So what are you saying?
The volume of the entire cylinder minus the volume of the hole that's cut out of it.
Yeah, so it's going to be like the volume of the pancake minus the volume of the hole. Exactly. And the hole is just another pancake, right? The hole is just another pancake. So we're going to have, basically what we're going to have is pi r outer squared h minus pi r inner squared h. So it's just you're subtracting out the whole. So they're both pancakes. So they're just gonna have, you're gonna have the outer radius. That's the one, the pancake you're gonna add. And you're gonna have the inner radius. That's the one that you're gonna remove. And that'll be the volume of that washer. Everyone follow? Okay. So what is our? Let's do our height first. What's the height of the washer? That's this thing right here, right?
Do you need corresponding H's for each?
Are they different? The height of the hole and the height of the pancake, are they different?
No. Oh, this distance, okay.
Yep, the height is this horizontal distance, right? Which is the same for both.
Okay.
Okay, so what is that?
Delta X.
Delta x. So our height is delta x. Check. Easy. All right, what about, so now we have R1, R outer and R inner. Okay, so here's R outer and here's R inner. So we got to go back up and look at this picture. figure out what is our outer. Our outer is, so a radius, we're revolving around the x-axis, so that's our center. So what is our outer? She wants 9. Agree with that? Is it always 9, or does it change throughout the thing? Does that radius change as we go across, change x, or is it always 9? No, it's always 9. Because look, it's horizontal, right? The distance from the x-axis along this whole thing always is 9. In another problem, it might change, but in this problem, that outer radius, if you look, from here to here, it's always 9. Okay, what about the inner radius? What's that?
9
Okay.
minus 6. No.
It's a y, right? That's just the y value.
Yeah, just x squared.
That's y, which is x squared. But you should see that as a y, that's the y value. From the x-axis to the curve, that's just y. Well, we know we're going to have delta x, so we need to rate it in terms of x, so it's x squared. Down here. Okay, so then we're going to have, so volume of a typical washer is going to be pi times our outer, we said is 9 squared delta x minus pi times inner radius x squared. That's the radius, but in the formula we need radius squared, right? So it's x squared squared. The radius is x squared. The volume of the hole is radius squared. We got it. We got our typical washer. And now what are we going to do? To get the volume of the solid, we're going to do integral. So it's going to be the sum of all the typical washers. The sum of the volume of all the washers. And each washer has a volume of 81 pi minus x to the 4th pi, or pi x to the 4th. And those are each, I'm factoring out the delta x, okay? So each of those is times delta x, and then the whole thing dx. Because now the washers are getting super, super thin. And now the question is, from what to what?
What times this? 0 to 33.
So where's our, so it's delta x, we're talking about the leftmost washer to the rightmost washer. It's x. So the leftmost washer is at where? 0. And where's the rightmost washer?
3.
It's going to be this one that has a, it's like just a ring, right? It's just a ring. It's like all hole and no washer. And that's at x equals 3. Where y is 9, right? Another easy integral to evaluate. So these really are about the setup, right? Question, please.
Could you just quickly talk through the radiuses one more time?
So did you see how, so you kind of have to go, you have to look at your typical washer and match it up here, right? Do you see where it is up here?
Yeah.
So there's your hole, and there's your that.
Yeah.
So the outer radius, if you look from 0 to 3, that outer radius is always a constant of 9. Even for the first washer to the last washer, your outer radius is always 9. It doesn't go up and down. It stays a distance of 9 from the axis of rotation. The inner radius changes, right? At first, the inner radius is 0, and then at the end, the inner radius is 9. So it's according to that curve right there. So it's the y value, the inner radius is the y value of that curve. Or x width. Better? Yeah.
understand how we went from that cylinder with the weird hole to the washer.
Because to get this thing, we gotta add up a bunch of typical elements. So the typical element is like if you took a slice of this, it's the washer, right? Or it's what you get if you start with the typical. This is why I really encourage you to do the typical strips on areas, because that's what you're gonna do here. You're gonna start with a region and do a typical strip, and then we're gonna rotate that region to get the solid. But then your element is going to be what you get when you rotate the strip. So if you take that strip right there and rotate it about the x-axis, you get that washer. And then all those washers added up from left to right make that solid.
Okay.
Is that better?
Yeah.
I appreciate the demonstration. In this case, wouldn't it be easier to do the negative space approach? If we just integrated from 0 to 3.
Yeah, then you would do that pancakes.
Yeah. Which 0 to 3 at x squared and then pi r squared h
I think it's about the same amount of work. But you have to understand. Yeah, I mean.
Well, computing the radii takes some mental gymnastics.
Well, so you're just doing just the whole, right? You just did this. You just did this much of it.
Yeah.
And then you had to calculate you had to figure out the volume of that whole thing by geometry.
Pi r squared.
Take that minus that. But I mean, if you notice, that's kind of what's happening here, because look, we just have a constant. So that constant is, if you integrate a constant, it's just like, it's the same thing everywhere, right?
Yeah.
So that in effect right there is what you're doing, but we're doing it in integral form.
That's really cool.
Yeah.
Wow. That is pi r squared h. Yeah.
Okay. Other questions? Do I have enough sheets? Feeling prepared today. I don't think I do. Well, maybe. Does anybody have a leftover sheet, a blank one that I gave another day? Here, we can just use full sheets. Yeah, that's fine. All right, so what I got one for you to do. So you can write this down along passing out papers. So it's the region between square root of x. Between the square root of x and x cubed.
Calculators, okay?
Sure. You shouldn't need a calculator for this. So it's the region between x cubed and square root of x, rotated about the y-axis. Yeah, y-axis. We got x. So between y equals x cubed and y equals square root of x, the region between those two curves rotated about the y-axis.
You want volume.
I want the volume of the resulting solid when you rotate. I'll write it up. Okay, you got 5 minutes. You have 5 minutes. Just set up an expression. Just set up an expression that calculates that volume.
Between y equals x cubed,
Y equals x cubed.
y equals x squared. Rotated about the
Express volume formed by rotating about the y-axis Okay? 5 minutes. You're just setting up the expression. Just setting up the expression.
Maintains this position, is it always just going to be the uppermost function minus the lower function for the radii? Like if they don't swim off.
No. I'll show you. We're going to do an example in a second.
Okay.
So you don't look for rules. Do them all. Do every problem on its own. Don't look for rules.
Oh, like if we're not centered on the origin, right? Okay. That's a cool.
Okay, I'll put that much up there, and we got to move on. So you can. Here's your typical washer. Outer radius x2, which is cube root of y.
Yeah.
That what you got?
Yeah.
Inner radius.
Say that again?
Outer radius is x2 is the cube root of y. Inner radius is your x1, y squared.
Yes.
We're gonna move on because we need to. I need to do an example, and you need to do another example. Agree with this? Does this agree with what you did? Okay. So let's look at this. Can I erase? Actually, I don't want to erase all of it. So now I want to express the volume solved by rotating about the, let's see. Instead of the y-axis, I want to rotate about the line y equals 8. The region whose boundaries are y equals ln of x x plus y equals 6, and the x-axis. All right, so ln of x looks like this. X plus y equals 6 looks like this. And then where's the line y equals 8? That's over here. Oh, x equals 8. I'm sorry, x equals 8. So we're going to take this region right here. Here's y equals ln of x plus y equals 6, and the x-axis, and I want to revolve it around x equals 8. So imagine that thing coming around and forming a solid. So over here on the other side, something like this.
So our direction of evolution will determine which variable we integrate with respect to?
Yeah, well, if you're using washers, yeah, if you're using washers. But you can also use the other variable. It's just a different. It won't be washers. We'll do that tomorrow. Okay. So first of all, what will this thing look like? It's going to look like this. Try it up here. Running out of room. I'll draw it. Try it here. Curved because of natural log like that. Yeah, this is pretty complicated.
Yeah.
That's a hole like that. Yeah, I got it. That's pretty much it. So it's like a football tee. It's like what would hold a football, but this thing would not hold water, right? If you try to put water in it, it would just flow right out the hole at the bottom. There's a hole at the bottom, right? There's a hole, okay? But it would be like a football stand. American football.
What are those called?
That?
What are those called? Are they called tees?
I think they're called tees. Yeah. So it's a tee. It's a tee for a football that would not hold water. Water would just pass right down through the hole at the bottom. Okay, so we're going to do our strip this way. And when we rotate that around the line y equals 8, we will get a washer, yes? We'll take our typical strip, rotate it around y equals 8, and we'll get a washer. And then the first washer will have the smallest hole. It'll be the widest washer with the smallest hole at the bottom. And then as we move up, the washer will get more narrow, and the hole will get wider. So the different washers, so the washers as you move up, the stacking washers, will get smaller according to natural log of x, but the hole will get bigger according to x plus y equals 6. So then our typical washer will look like one of these guys. There's our typical washer. And so it's going to be volume of the washer will be, again, volume of the pancake minus volume of the hole. Which will equal pi r outer squared minus h, sorry. Pi r outer squared h minus pi r inner squared h. Here goes. Outer radius. What's the outer radius? So back to our first original sketch. From where to where is the outer radius? Well, ln x has to do with it, but it's from here to here. This is our outer. Do you see that? So you're the center, you have the center of rotation, and then yes, ln of x defines the end, but that's not ln of x. Our outer does not equal ln of x. What does our outer equal?
8 minus e to the y.
Tyler says 8 minus ln of x. It's 8 minus x. This is x. So our outer is going to be 8 minus the x coordinate.
Okay.
So not ln of x, right? So what is x in terms of y then? This is y equals ln of x. Now we need what the x is in terms of y. X equals? E to the y. So this outer radius is?
8 minus e to the y.
8 minus e to the y, and then we're going to square that. Everyone catch it? So first of all, that distance is not, it's not x, it's 8, x2 minus x1, right? So think of x2 minus x1. x2 is 8. x1 is x coordinate, the x coordinate on this curve, which is the curve y equals ln of x. So solve for x is e to the y. So the inverse inverse. Inverse of natural log is exponential function. All right, what about the inner radius? So the inner radius, I'll do it in blue,
8 minus 6 minus.
is this from here to here. That's our inner. Which equals 8 minus,
6 minus 1.
it's also an x-coordinate, but the x-coordinate on the line. So it's 8 minus x, but now for this, so what does x equal?
6 minus 1.
6 minus y. Which turns out to be 2 plus y. Can we simplify that, make it easier on ourselves? So this 8 minus 6 minus y is going to be our inner radius. I'm going to change that, it's going to be 2 plus y.
Squared.
And I forgot h. What is h in this case? Delta y. So I'd recommend in your notes, write this 8 minus 6 minus y here. Like I'm going to do it. I think that's, for looking back in your notes, that's going to make more sense.
But then we can simplify it before we.
You can simplify it, but I just want to, for meaning's sake.
Yeah, because then we should find out.
Yes, but before you square that out, do 2 plus y.
Okay.
2 plus y. Okay, then the integral is, the only thing left is the bounds on the integral. It's going to be the lowest washer up to the highest washer. So y equals 0 to
Natural log of 8.
so we have to find
Intersection.
intersection point,
Oh.
right? Intersection point. So natural log of x equals x plus 6
X minus 6 minus
which you're going to do in your calculator. Use intersection on your calculator.
Yeah, that's hard.
If you're not doing minus, maybe that's plus 1.
But you need the y value, right? So once you find that x value, it's going to be that. You're doing y's, right? So you're finding the x value of the intersection, and then you're going to add 6. And that's your y value.
Why do we have the positives?
What?
Why is it?
Oh, it probably should be, right? What is it? Y? 6 minus x, sorry, 6 minus 6. Right? Hopefully you all were thinking that. Because we're setting y is equal, right? So y, natural logs equals 6 minus x. 6 minus x. And then you're going to use the intersection, get that x value, and then the y value will be 6 minus x. And that's going to be your upper bound on.
It's like 4.5.
This is 4.5?
Yeah.
Let's do one more decimal place. 4 point.
It's 1.50.
Okay, 1.50 what? Let's just a little bit more than just 4.5.
1.50333.
Okay, so 4.407.
Wait, no, we're looking for the x. I'm sorry. 4.497 is the x. So
Okay.
6 minus x.
Yeah, just get the y value from the intersection. We want the y value. That's what we want.
So it's 1.503.
Okay, so it's going to be integral from 0 to 1.503. of this dy instead of delta y. Okay, I was going to have you do one more of these. We're out of time.
What's the homework?
Homework is Weber, just Weber.
Okay, thank you.
Okay, the key to these is the picture. These are geometry problems. You have to make a good picture and do your typical elements, right? Make your typical washer in order to figure out what the volume is. Happy Monday.
Thanks.
See you tomorrow. Yes, just right there on the overhead is fine.